Hi, I'm Vinod. I'm a partner software engineer at Microsoft and one of the committers of Microsoft's DocumentDB. And today, I'll be talking about designing document databases for PostgreSQL, aka how we leverage the awesomeness of Postgres' extensibility model to build Microsoft's DocumentDB. Okay, so that is a very long title, but what does it even mean? So, what are document databases? At a high level, document databases are primarily a category of NoSQL databases, which are basically focused on scale up and scale out. So the premise is being able to scale out to more than what one machine can do. And so focus on very small, tiny databases all the way to large data sets that can be several hundreds of terabytes. Right. But specifically, these are a category of NoSQL databases that focus on schema-free documents. So JSON, JSONB, BSON, and so on. And because we're looking at scale-out systems, they typically provide a subset of traditional SQL features. So like lesser transactions, joins, and stuff. But over time, they have been adding more and more of these features to provide better distributed transactions and transactions in general, cross-document joins, and better isolation semantics. Now, specifically, what am I talking about DocumentDB? DocumentDB is the backend that powers Azure Cosmos DB for MongoDB vCore. This service is running a Mongo compatible protocol in Azure. And the backend for it is powered by DocumentDB, which we recently open sourced. As part of open sourcing DocumentDB, we managed to map some of those API semantics to Postgres query semantics. The interfaces were built on similar contracts to what we had in the service. And one of the things that we wanted to do was embrace the ease of use that we got with our service. In other words, you didn't have to deal with table creation, schema management, and all of those complexities that you tend to do when you're dealing with databases. We also wanted to draw inspiration from some of the other work that we've done internally that on other NoSQL databases in terms of how we do easy index management, dealing with wildcard indexes and so on, and how do we deal with filters, sorts, and things like TTL, which purge documents based off of some expired. And because this was based off of the MongoDB vCore service, we had to use BSON as a storage layer. And this was primarily done from the perspective of type system fidelity and reducing the transcoding cost for I/O. And that's super important when you're dealing with things like OLTP workloads, which are low latency and high throughput. And JSONB technically could have worked as well, just as fine, except we would have had to pay for the transcoding costs. And given that BSON was already binary encoded, we figured it was just as well. So getting into it, we talked about the ease of use of the service and how we wanted to bring that into DocumentDB. The insert command in this case, which is what you see on the top, is how you interact with the system when you first come in. Notice that you don't have to create a table, you don't have to declare a schema. You just come in, open a shell, and type insert one. And in this case, I'm inserting to a collection that is called Cafe, and I'm inserting a simple document. And in this case, it detects that there is no collection called Cafe, creates the collection automatically, and inserts the document on my behalf. On the bottom left, you can see the schema that is there for a document table in Postgres. And as the red pointer shows, there's only 3 columns in the table. There's a shard key and the object ID, which form the primary key that are going to be accessing the document, and the document itself, which is just a BSON blob. We modeled the BSON type very similar to JSONB. In other words, it had all of the properties of JSONB, like toasts and compression and so on, so that we could leverage a lot of what was already built into the Postgres infrastructure. You'll also notice that there's this thing called collection ID, and the table doesn't really match the collection. And we had a mapping table that mapped the collection to the Postgres table. And that was primarily due to naming differences of what was allowed in our service versus what Postgres allowed. Now, let's get into the fun stuff. Like, how do you build queries? How do you think about issuing aggregations and so on in DocumentDB? In our very first generation of queries, when we first started the service, we were looking at it from the perspective of making stuff look very much like SQL. So we had our incoming request. We would translate that to something that very much resembled a SQL query, which is what you see in the first query up there, which is you have a projector, you have a from clause from a collection instead of a table, and you have a filter. And this worked very well initially. But once we started building more and more features, it started becoming more and more cumbersome to debug and figure out where all of these complex aggregation queries were going. For instance, if you look at the group by, there is the max of some expression to extract a value from the JSON, and then you have to, or BSON in this case, and you have to filter it, and then do another group by on some other expression that you have to extract from the BSON document. And again, this is not too bad. But as we started looking into even more complex queries, for instance, this query is called a lookup, which is basically doing a cross-collection join between two collections, the orders collection and the inventory collection, and matching the local field item to a foreign document ID, and storing it as a field called match documents. And in this case, this simple one-line pipeline became this 8-line SQL query. And that was primarily from the perspective of managing, extracting the fields, doing the join, and making sure that appropriate things could be pushed down to various indexes. And this is still fine, but as we added more stages and nested pipelines and subqueries, things started getting very difficult to debug and manage within the service and figure out where we went wrong. Additionally, from a performance standpoint, we were also translating from the incoming BSON that was coming in to a SQL text query, and then to a Postgres query plan on top of that, which added overhead to the query layer. And we couldn't even use prepared statements because we didn't know what incoming user queries were there, and they were fully dynamic. So given that, we built our second generation of queries where we decided to remove the intermediate SQL text generation layer. And so the query basically looked like selecting a document from the aggregation pipeline, and you provide the actual pipeline declaring the intent directly in the query. And how did we manage to do that? Postgres had an extensibility layer that was built exactly for this. There is a planner hook that is available in Postgres that allows you to replace the default planner that Postgres uses to plan queries. And in our case, when we saw this specific function, and you can see where we query has aggregation function here, we basically expand that aggregation function directly into the query tree, avoiding the SQL query text altogether. In some cases, when the query is simple enough, like a point read, we know exactly what the plan statement is because we already know that we pre-created our tables with primary keys. And in this case, we bypass Postgres' plan altogether and we just direct it to an index scan against the primary key. In other cases, we just delegate it back to Postgres and we get to leverage all of the amazing innovations and improvements that happen in Postgres while just subbing out one tiny layer that generated SQL query text and replacing it with the query tree. And one of the things that we got out of this was we were able to get a 50% improvement in cases like simple scans relative to the case where we basically had to parse the SQL query and send it to the backend, just because we were also able to prepare the outer envelope in the Postgres backend at this point. So we're able to generate the queries. We're able to push it down to Postgres. Now, how do we use indexes to optimize performance for these queries? A little bit of a primer before we get into it. Because this was based off of our managed service, some of the query semantics that we had to reflect came in from that. And one of the interesting query semantics we wanted to respect was when you have a filter, the filter does traverse into arrays within the document. In other words, if you have a filter a.b equals 1, that technically matches a document which has a nested object with a value 1, or a nested object with an array of 1, or an array which has a document of b is 1, or an array with a document which has an array which is 1. In other words, every first generational array is traversed as part of traversing a path into a filter. In another way, if you think about the document A, which is an array of 1, 2, 3, technically that matches all 4 of these filters. A is 1, A is 2, A is 3, and A is the array 1, 2, 3. From an indexing perspective, what this meant is that the indexing must support multi-valued indexing. In other words, every document can technically produce multiple terms that can match multiple queries for a given path. And that becomes important when we start talking about which indexes to pick and how we push down to the index. Additional constraints that we had to work with is we needed to support things like wildcard indexes. Now, wildcard indexes are very popular in document databases and NoSQL systems because they allow for dynamic schema evolution. In other words, you can create one index, and as your schema changes, you don't have to go and revisit which indexes to create and what to manage for performance. Anything that's created in the scope of a wildcard index will still support all new evolutions of the schema. So this is already there in some extent to for JSON in Postgres with JSON path indexes, where you can create a root wildcard index against a JSON document, and then you can issue JSON path queries against any subtree within that document. So consider this case in DocumentDB, where you have a filter a.b equals foo. Technically, that filter can be pushed against all four of these indexes. In other words, an index on the single path indexing just a.b, a root wildcard that indexes the entire document, a path-specific wildcard that is indexing just A, or path-specific wildcard that indexes everything under a.b. Right? So when each of these wildcard indexes get created, a single index needs to be managing multiple paths and multi-value again. And the other requirement that comes in out of that is that when you author the query, you want to write exactly one filter. In other words, you just want to declare the filter as a.b is foo, and you want the query system to be smart enough to figure out what is the best index to push this down and push it down correctly to the index that satisfies that query. Beyond that, we also wanted things like unique constraints to work and TTL indexes, which are basically indexes that purge old documents based off of some expiry time. And of course, this goes without saying that we wanted all the core query operators to be pushed to the index layer. So what does that give us? We took a look at all of the different Postgres indexes that are available today. Initially, we started with considering the B tree because that's generally widely used in the ecosystem. It supports unique constraints and order by, and it's very popular within Postgres. And this worked fine for unique, but one of the big things that we found was that the B tree layer does not have operator extensibility, and nor does it have multi-value support. And given our requirements for wildcard indexes and how we traverse into arrays, we could not use B tree to satisfy our indexes. So then we moved on to Gist. Gist technically can support unique constraints via exclusion constraints, and it does have operator extensibility, but we once again found that it doesn't have multi-value support, and so we had to discard that as an option. We then looked at the Gin index, which was great because it had really good operator extensibility, and it had multi-value support built in, and it could support our wildcard indexes. And so we started building our indexes initially on top of Gin when we realized we could not support unique constraints in any way. And at that point, we found this open source extension called Rum, which was based off of Gin at some point, and that added support for unique constraints with exclusions into the basic indexing layer. And so given that we had all the operator extensibility, multi-value support, and wildcard support, and exclusion constraints, we picked Rum as the backing index for DocumentDB. Beyond that, TTL was built using another open source extension in the community, pgcron, that allows for periodic running of batch jobs so that it could consult the index for what documents needed to be purged and purge any expiring documents. So we have our indexes. We know that you can use the operator class extensibility to push it down. But how does that exactly work? So especially for Gin and Rum, it allows very structured extensibility, but it allows you to author functions that can push any kind of query predicate to any kind of indexing structure, right? And it has 4 extensibility points that we have to consider. The first one is the extract value function, which is called on every insert and update that allows you to declare how to produce terms that will be sitting in the index. In other words, you get a callback with the document, and you get to produce the exact set of terms that will be stored in the index that you can query later. And you can produce as many of them as you want. Then when a query comes in, the first callback you get is the extract query, which basically maps the query predicate to index terms. So you can see that in the first example here, where you have a.b is in 1, 2, or 3. The extract query can return 3 possible index terms to query for. ab equals 1, ab is 2, and AB is 3. And the gin layer handles, or the rum layer handles, making sure that it'll query the index against whatever you give it, um, and manage the rest of the layer of the query. The next extensibility point that is given is compare partial. And this is an optional check. Not every operator needs to support this. But if you're doing ranges of scans, it will basically walk the index tree and call back and say, does this document match your scan? Or does this document match your scan? And that can be seen in this next filter we have, where we're saying, give me all the arrays that are in A.B, where the size of the array is 5. So in that scenario, you can say, my extract query will just give you the smallest array. And so you can start scanning from the smallest array onwards that is rooted at A.B. And then for every array that comes back, I can just check the index and to see if the array's length is 5. Right? And that allows us to basically just filter subsets of documents and load very few documents in the runtime and do as much work in the index as possible. The final check that we get is a consistency check, which is, given all the terms you asked me to check and given whether they match or not, does the outer row actually match the query? So in the case of in, if any of the individual index terms match, that means the outer row must match too. In the case of $size here, if the compare partial returned true, it must be true. And therefore, the outer query matches. And this way, you can build extensibility into how you build the index terms and how you query the index terms without having to touch Postgres at all. And this is all extensibility that is built in. So now we have our operator classes. The next thing we needed to figure out was, how do you push these filters to the index? And this may seem simple, but it was actually more complex than we thought it would be. So the very first thing we did was we looked at the simplest thing, where we put the filter, we project out the path that we were going to filter against. And then when we were creating the index, we put the exact same filter there. So when we have this filter, Postgres will figure out that this expression matches the expression in the index, and therefore you can push down this filter to the index. And this is done automatically, given the appropriate off-class definitions. But there was a problem with this. It was unable to work with wildcard indexes because to Postgres, this expression must exactly match what's in the filter. And so the wildcard index that is on the root document could not match the filter on A.B because the root expression itself was different. Another smaller issue is that when there was no index and we were applying the filter on the runtime, you first had to project A.B out of the document, produce a new document, and then evaluate the filter against that projection, which added a slight increase in cost, especially when we were looking at large documents, which we'll see an example of in a bit. So this didn't really work for wildcard indexes. So we started thinking, what can we do? The next layer we thought about was, okay, what if we don't put the filter definition on the left side of the operator and we put it on the right side? So all our filters were where document equals, and then we specified A.B as 1. Now, the index expression here on document matches the filter. And within the index, we put the op class options, which is another layer of customization that we were given within the gin or rum indexes, to specify the paths that we wanted to index. So this first index would only index terms that are below A.B. And the second one will be a root wildcard, and the third one will be only under B.C. So at this point, we figured, oh, cool, like all these filters could be pushed to appropriate indexes. And the runtime evaluation no longer needs that extra projection, which is even better for perf. But there was a problem with this again. Now, our entire index selection process was broken because through Postgres, this expression matches all 3 indexes, so it's free to choose any one of them. So this filter, technically, which is on A.B, could technically be pushed to the B.C index, producing incorrect query results. So we were still off. And we were still trying to think about what to do next. So then we landed on the third approach when we spotted the support function that is available with every function execution. And this is a planner function that you can register with every filter. And you get a callback during the planning phase with this struct, which has your filter it has the index, it has the op family that the index has, it has all of the options that the index has associated with it, and you get to return what you would push down to that index fully in code. So in this case, you can also, by the way, declare whether that filter is lossy or not, or whether it can produce an exact match. So we basically built our filters to be Beeson dollar equals, which is the Funka expert equivalent of the operator you saw earlier, with the document and the filter. And we built our indexes the same way we would before. But now inside the support function, we would introspect into the op class to look at the index path, figure out if it matched the filter, and only if it did would we push it to that appropriate index. So at this point, our runtime evaluation does not need an additional projection. And with the support function hook, we were able to fully provide an exact match to the index and only push to the index that can be satisfied by the given query. So this sounds all great, but there was still one more problem with that, which is even though it pushed to the index, it still evaluated the runtime functions even after it matched all of the things in the index. And why is that? And you can see the example right here. So I ran an explain for something that is a filter that matches on vehicle ID. And you can see a bitmap index scan on the vehicle ID index, with the index condition being something that got pushed down to the index. But you still see a runtime filter applied here. And it applied it against all of the documents. And given this was a relatively large set of documents, it has to decompress them, project onto it, filter it, and redo the work, which the index already did. And so you can see here that the index time was only 66 milliseconds, but the overall time took 30 seconds for this query. So we had to think, okay, what can you do here? And here Postgres once again had an extensibility point that helped us. And to the top right, you can see what went wrong. During planning, when it's about to form the execution phase, Postgres looks at all of the scan clauses that are available in the where clause, looks at all of the index clauses, and says, if the index clause is implied by the runtime clause, then I can strip it because it's provably implied by the index qualifiers. However, Postgres doesn't know about the fact that we use a support hook to introduce an equivalency. It doesn't know that those two are equivalent. And so we had to add the filter in. But there is another hook available in Postgres called a rel-path list hook. And this hook is called after planning and on the base table, after it's done all of the index path selection and everything, but before execution actually starts. And before all the group bys and order bys are figured out. And in this case, what we did was we added ourselves into the hook and we rewrote the expressions that weren't pushed out to the index in a manner that this loop that is removing provably implied qualifiers can then remove it. And so this one additional hook saved us in terms of the performance. And you can see that here. On the top, we have the same explain that you saw before. It was 66 milliseconds on the index and a whole 30 seconds on the runtime end to end. And once we did this rewrite, you can see that the filter now becomes a recheck condition. And a recheck condition is something that is only evaluated when the index says it is lossy. In other words, if the index cannot fully correctly evaluate that filter and it needs a runtime recheck to make sure that that thing really matches. And in this case, you can see that the index took around 63 milliseconds again, and the overall time was only 136 milliseconds because it didn't need to load all of the documents and reevaluate the filter. So once again, we had an extensibility point that was there in Postgres that saved the day. Now, we've talked a lot about a bunch of these hooks that we put in, the index filtering and so on. But one of the things we did is, again, we used Beeson instead of JSONB. And the question is, how much of an overhead is that? We also introduced these custom queries, and we had to basically add planner hooks to do the planning. So how much overhead is all of that? So I happened to run pgbench against some simple queries against JSONB, against Beeson that is directly run as a prepared SQL statement, and using the DocumentDB wrapper functions. So you can see that they're all roughly within the ballparks of each other. So point reads, JSONB and Beeson work hand in hand, and the DocumentDB find wrapper takes more latency, which we are working to improve. But it is in the comparable range for each of these. And it's a similar story for count and for runtime filters, where you're returning a projected field that matches a runtime filter. And while it is true that JSONB is still better, and I don't think we can compete there, but we can get it pretty close, and that is what we're trying to do. Overall, I have to say that Postgres extensibility is awesome. And as we were building DocumentDB, whether it was building queries, whether it was trying to figure out how to push down the queries, whether it was figuring out which indexes to use, whether it was figuring out how to push it to the index, we always found an extensibility point in Postgres that helped us move forward. Thank you.